So just like we have difference of squares, that's a special kind of factoring problem, we have certain problems that deal with cubes. Just to kind of reiterate, in case you're not familiar, cubes would be, for example, like 1 times 1 times 1. Whatever you get, that's a cube. So the first cube is 1. And then if we do 2 times 2 times 2, we get 8. 3 times 3 times 3, or 3 to the third, 4 to the third, 5 to the third, etc. So I want you to go ahead and make a list of your cubes because these are numbers you want to have memorized. So we have 6 cubed, 7 cubed, 8 cubed, 9 cubed, and 10 cubed. If you know 1 through 1000, you're probably pretty good. I will tell you the most common ones are 1 through 125. Those are the ones that you'll see the most often, but these do occasionally pop up, so it's just not a bad idea to have them on your radar. So when we think of perfect squares, hopefully you're thinking, okay, 1, 4, 9, 16, 25, etc. We want you to have the same idea with cubes. So if we see numbers like 27 or 64, we want to register, hey, that's a cube. There's probably a pattern that's going on here. So that's the first thing. You have to have your cubes pop out to you when you see them in a problem. So if we have two cubes that are added together, so if I like wrote 8 plus 27, these are two cubes. They can actually factor in based on this formula. So you're taking basically the cubic root of the first and second term, and then you take the square of the first, you multiply the two terms, and then the square of the last. So it just takes some practice using that formula. So the first thing you want to do is realize, okay, 64, that's a cube, x cubed is a cube, and 1 is a cube. So we have ourselves a sum of cubes. So we want to go ahead and use our sum of cubes formula. So the first thing we want to do is recognize, well, what would a be? In other words, what to the third power gets me 64 and x cubed? So the way to go backwards from that is just simply take the cubed root. Just like a square root undoes a square, a cubed root undoes a cube. So we're going to cube root the 64 and the x cubed, and we're going to get 4 and x. So if you take 4x times 4x times 4x, you get 64x cubed. So this is the cubed root of that term. We want to do the same thing for b. So we want to take the cubed root of 1, which of course is just 1. So that's the first thing you have to establish, is who is a and who is b based on this formula. So just cube rooting. And then we're going to go ahead and set up our formula. So it says we're supposed to add a plus b. So we're going to do it 4x plus 1. And then we want to square a. So 4x times 4x is 16x squared. We write minus a times b, which is 4x. And then we finish with plus b squared. And b squared is just 1, so we write plus 1. That is completely factored. You could always see, if you can factor the quadratic, but so far I have not met a cubic problem that factors even further, unless there's a GCF, but there was no GCF. So we'll try it again, and this one I really want you to recognize, well, hold on a sec. 16 is not a cube, and neither is 54. But before we even do that, we have to remember step 1 is always factor out the GCF. So I can factor out a 2 and an s cubed from this problem. So we want to start with that. If we factor out 2s cubed, we get 8s cubed plus 27. So now I kind of block out the GCF. I'll keep it in the problem at the end, but I really want to focus on what's in the parentheses here. I realize right off the bat 8 and 27 are cubes. So I can actually use the sum of cubes formula to further factor these parentheses. So if I take the cubed root of the first term, I'm going to get 2s. And if I do the cubed root of the second term, I get 3. So I'm going to go ahead and set up my formula. 2s, or a plus b, so 2s plus 3. We're going to square a, so 2s times 2s is 4s squared, minus 2s times 3 plus 3 squared. So we just don't want to forget that this all gets you back to here. However, if I want to get back to here, if I multiply your answer together, I should get what I started out with. You need to put the GCF in the problem. So you need to make note that, oh, the 2s cubed is still there. It didn't go anywhere. I just knew I could factor by parentheses even further. So the GCF just kind of comes along for the ride. So just like we have a sum of cubes formula, we have a difference of cubes formula. It's almost identical, except if you compare the signs, we start out with a minus and then a plus. Everything else is the same. So I see 125 and I'm like, oh, that's a cube. So I can use the difference of cubes formula. So if I take the cubed root of the first term, that would just be x. And the cubed root of the second term, don't worry about the sign. The sign's covered by the formula. Just focus on the number. The cubed root of 125 is 5. So then we want to set up our formula. A minus b. A squared. This time it says plus bx, which is 5x. And then it'd be plus b squared, which is 25. And then we'll just do one more. So if we take the cubed root of each of these, because I recognize they're cubes, I get 3x and 2. So these are what I'm going to be substituting in for a and b in my formula. So we subtract them. We square a, we multiply a and b, and then we square b, and our signs are just going to be looking like minus, plus, plus. So really the big difference between these two guys is you have minus, plus, plus, and plus, minus, plus. That's it. Everything else you do the exact same. So we definitely want to be on the lookout for cubes. Just like we're on the lookout for squares, we want to recognize cubes. Alright, method 3 is grouping. We've kind of done grouping in the past where we use the X method with grouping. But in these problems, you can see there's already 4 terms. So what I would do, because it only takes a couple seconds, is I would go ahead and group it up. Pair up the first 2 and the second 2. I'll just put a plus here so I'm not really changing the problem. And I'm just going to pull out a GCF and hope my parentheses match up. So I could pull out z squared, and I'm left with z plus 5. And I could factor out negative 4, and thankfully I'm left with a z plus 5. So sometimes we get lucky and it actually works. Now there's other times where we try this grouping and our parentheses don't match up. It doesn't mean the problem is not doable, it just means the grouping's not going to work. It's not going to get you anywhere. So we're going to go ahead and pair up our GCFs, z squared and negative 4, and keep our z plus 5. And again, on the lookout for squares and cubes, I see 4 is a square and z squared is a square. This is a difference of squares. So I can change this to z plus 2 and z minus 2. And so that's my answer. If we try grouping with our next example, GCF for the first group would be, I'm going to write it over here, x squared, and then you're left with 4x plus 13. The GCF for the second group would be 3, which leaves you with 9x plus 3. So you can see the grouping didn't work out for us. That doesn't mean that we can't do the problem, it just means we have to find a new tactic. So if you notice, they give you a hint down here and they're telling you, hey, if you put negative 1/4 in for x, you're going to get 0 as the answer. What that means is negative 1/4 is an x-intercept, so that means that it's going to work if you use negative 1/4 for synthetic division. So I'm going to go ahead and I'm going to write 4, 13, 27, 6. And the 0 is negative 1/4. So remember, when you're doing synthetic division, if you get a remainder of 0, that means that this number was an x-intercept. So we know that this is going to work out because they told you you're going to get 0 when you plug it in. That means you're going to get a remainder of 0 when you divide by it. So bring down the 4, we multiply, we get -1. Then we multiply again, we get -3. Do it one more time, you get -6, and there's your remainder of 0. So my answer would look like this. It would look like 4x squared plus 12x plus 24. However, they didn't actually ask you to divide, they just asked you to factor. So you have to show that this polynomial times x plus 1/4. Remember, you would take this and make it equal 0, and that's the number that goes out here. So that's what you have to put in your answer. If you multiply these two together, you get back to this. Now, the only thing is, it's not really considered proper to have a fraction inside a polynomial. When we talk about factoring, we always want to have whole numbers. So there's a way to get around this issue. You have to realize that 4, 12, and 24, that's not completely factored. They share a GCF of 4. So I'm going to factor out a 4 from this parentheses really quick. And then what I'm actually allowed to do is I can go ahead and multiply this 4 times this parentheses. It's multiplication. Order doesn't matter. And if you do that, you'll notice your fraction goes away. So now I have 4x plus 1, and then I have that x squared plus 3x plus 6. And then I'm just running through, and I know there's nothing that multiplies to make 6 that adds to make 3, so I know that I'm truly done, that this does factor into that. So in my next lesson video, I'll go ahead and take you through the last method, and then we'll do some mixed practice just to kind of summarize it all.